This video, I'll be demonstrating the use of overset and dynamic meshes with the volume of fluid or VOF model. This simulation is of a simplified lifeboat launch. The lifeboat is being launched from a height of just over 100 feet, and we're using Fluent to predict the linear accelerations experienced at the bow and stern of the lifeboat. I'm starting with the background and component meshes already loaded. Here's the boat and the component boundary, which is defined as an overset boundary, as you'll note here in the tree. This diagram of the problem description shows the 39-degree incline of the boat, its starting height, and the initial velocities in the y and z directions. You'll also see the two locations where I'm monitoring the lateral acceleration. Note that the boat is the origin for the global coordinate system. I'm going to stick with the default donor priority method of cell-based. Now I'll initialize to establish domain connectivity. Displaying the mesh with overset enabled and just the background and boat, you can see that the mesh has been preserved around the boat. I'll enable the VOF model with the implicit body force option. I didn't set up this case with an inlet or an outlet, so I'm not enabling open channel flow or waves. Here you'll note I've already created water as a material, so Fluent automatically assigns air as the primary phase and water as the secondary. I need to specify the operating conditions for this case, which includes enabling gravity. I've enabled the 6 degrees of freedom solver and implicit update, which updates the dynamic mesh during the time step, resulting in a stronger coupling of the flow solution and the mesh motion. I've defined two dynamic mesh zones for this problem, one for the boat and one for the component zone. Besides this passive option, which is enabled for the component zone, the settings are the same between the two zones. These values are as I showed in the problem description earlier. The UDF selected here looks like this. It defines the mass of the boat and its inertial properties. There's also information for automatically calculating acceleration at the monitor locations noted in the problem description. Here's a look at my solution methods and the solution controls. Note that here in the initialization task page, the water volume fraction is 0, meaning that currently the domain is filled with air. Now I'll patch the water into the system. To do that, I'll first create a region register. The important number to note here is the negative 31.4 meters, which is for the height of the boat above the water surface. Now that I've got a register, I'll open the patch dialog box, select water as the phase. The volume fraction of water is 1, because the region defined in the register is 100% water. And I'll select the register I just created. Here's what the problem setup looks like now that it's been patched with water. Now I've completed the setup, so I'm all set to start Fluent calculating. Here are two animations of the solution. You'll see how the bow of the boat experiences rapid deceleration after impacting the surface of the water, which initiates a rolling moment, causing a steep acceleration for the stern. The lifeboat then comes out of the water before re-entering in what is known as the slamming effect. This concludes this demonstration of dynamic overset meshes and the VOF model. Thanks for watching.